Hi, my name is Amy Sullivan, and I'm the current president of AAAR. It's my pleasure to welcome you to our 36th in our monthly AS&T lecture series. So this is a new initiative for AAAR being supported by the Freelander Memorial Fund. So each month, a high-impact paper from our journal, AS&T, is selected by the editors to be presented by its authors. With these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities, and also give us a chance to all come together outside of the annual conference. In addition, these lectures are being hosted by our student chapters, and we are also recording them, and the recordings will be later posted to our AAAR YouTube channel, which you can access from the AAAR website under the Events tab. I want to thank everyone who's helped to make these happen and for all of you for joining us. And with that, I'll turn it over to our student chapter from the University of California, Riverside to get us started. Thanks.
Hi, everyone. I'm so excited and honored to be introducing this talk today. My name is Erin Bowie. I'm the current student chapter president of AAAR at UCR. And this is a really interesting subject of conversation to me. So Dr. Asa-Awuku has done so many amazing things in atmospheric research and in academia and sciences overall. I'll try to keep it brief, but know that there's so much more incredible work that she's done. So if I don't mention about it here, feel free to explore for yourself. But initially, she graduated from MIT with her bachelor's in chemical engineering and then moved directly into a PhD at Georgia Institute of Technology, where she started studying cloud condensation nuclei activation and the complex dynamic relationships between the formation, growth, and properties of cloud and cloud-like droplets. And I understand that this is when she really began aerosol research, especially into the chemical composition and behavior of cloud droplets and their solutes. And these topics of the interactions between aerosol behavior and water in the atmosphere really maintained as a major theme in Dr. Asa-Awuku's work during her postdoctoral work at Carnegie Mellon University, and then also at UCR, where she held assistant and associate professor positions until about 2016. So we're super excited to have her back and hosting this talk today. And she's now a professor in chemical and biomolecular engineering and associate dean at the University of Maryland College Park. Congratulations, awesome position. And Dr. Asa-Awuku also holds several honors and awards. Big lists are available of these, but I wanted to highlight that she not only served as the president of AAAR in 2022, but it was the inaugural recipient of the new Teaching, Mentoring, and Training Award by AAAR. And her work into youth involvement in sciences and atmospheric sciences is really admirable and much appreciated. So she's constantly doing work developing our understanding of particle transport, formation, and resultant climate effects. And it's really awesome stuff. In the talk today, especially, the subject of suspended micro and nanoplastics is currently very relevant. I think it's on a lot of people's radars, and the hygroscopic properties of nanoplastics is a facet which still needs a lot of development and exploration. So with that, I will turn it over to our wonderful speaker to tell us about it herself. Thank you.
Thank you for that wonderful introduction, Erin. It's such a pleasure and honor to be hosted by the UC Riverside Student Chapter. I remember it was the first student organization officially recognized by campuses for our AAAR student chapters. So that was done many, many years ago, and I'm glad to see that it's still thriving and new and more excellent students are joining in our AAAR ranks. So with that, I will start the talk, which is about a paper that we published in Aerosol Science and Technology in 2024 regarding the hygroscopicity of nanoplastic particles. And so before I get into the real technical detail, I wanted to set the stage for this work and how we got into it. To do that, I'm going to ask you all to do a little meditation exercise. That is, I want you to think about an opportunity to visit the far lands of the Earth, right? These remote regions, let's say Antarctica and Arctica, so hopefully in the spring, of course, when the weather is nice. And so this image, there's blue skies, you can see this freshly fallen snow, and you have the opportunity to visit this location. And at this location, you love snow so much that you're curious to figure out, I wonder what's in the snow. So you gather up some of the sample, right? You take it back home with you, and then you run it through some analytical devices. And you find out that within this freshly fallen snow, there are microplastics. So this actually happened to a few researchers roughly 5 years ago. They were able to look at freshly fallen snow in the Arctic, and they found that it contained microplastics. Significant amounts of microplastics, on the order of 10,000 per liter, was in this freshly fallen snow. So the question now becomes, how? How do you get microplastics in such a remote region? What we know about plastic pollution is that there's a lot of it that's been forming the oceans. But what we really now know is that plastic pollution has no borders. Even in these remote places, we can find remnants of plastics and human anthropogenic effects. Okay. And what I love about this idea of how does it get there is that we want to know fundamentally the processes, right? As scientists, how do you end up with materials that we know are man-made in such a remote area? It's this curiosity and it's the necessity of fundamental science which drives our field and which drives science in general that we want to explore. Okay, so let's get a little deeper. To get a little deeper, we need to start in the beginning. And so what are plastics? Well, plastics are from the Greek word plastikos, meaning moldable, right? And it is a term that we use quite often to describe synthetic or human-made polymers. Polymers are essentially large macromolecules of repeating units called monomers. And so one unit is a monomer, several units are oligomers, and polymers are known to be hundreds of these units linked together. And I'll come back to that by the end of this talk. So polymers have been used for several centuries, right? We know the first polymers were actually used by Mesoamericans, that's Central America and Latin America, and they used it to make natural rubber. Natural rubber they used for games. They made little balls like we still use today, but they also used it in textiles to make it waterproof. We also have other indications that polymers were used in history. That is, there's a poem, an Indian poem that describes the use of shellac. And shellac is essentially a polymer that we put on different materials to make it waterproof. And in this Indian poem, they talk about this beautiful castle that was, or I should say palace, that was shellacked to preserve it, right? And this is a poem from 1000 BC. So we've known about polymers and we use polymers forever. So those are natural polymers. But when you talk about man-made or synthetic polymers, we think about plastics, right? And so the age of plastics really starts in the 1800s, 1900s, right? 19th and 20th centuries, right? We know that polystyrene was discovered by a German apothecary, Edward Simon, in 1839. We think about Charles Goodyear, who vulcanized rubber for tires, and that patent's in 1844. There's also another patent in the UK around that same time as well. We think about PVC, nylon, polypropylene, Kevlar in the 1960s. And so we know the use of plastics really took off in the 1950s. And lastly, I note polymer banknotes, which are used by many countries today for money, right? So polymers are in everything that we do. They're everywhere. And why? Because quite honestly, they're really useful, right? They're moldable, they're durable, they're lightweight, they're versatile. We've known that they're non-biodegradable, and so we know that they help preserve life, right? Hence why we shellac things. We use them all over the place, right? From packaging to construction, automotive, and electronics. They're very useful. So there are two main categories of plastics. There's thermoplastics like polyethylene and polypropylene, which you probably interact with many times a day if you recycle. And what's nice about these plastics is they can be melted and reshaped multiple times. The second is thermosetting plastics. These are plastics that essentially harden permanently after being molded. And so I found this image of epoxy used for flooring and design. You can see that it glows in the dark, epoxy. So these plastics are also used to decorate and are used for art, in addition to things like construction. So plastics are everywhere, right? And quite honestly, they have revolutionized modern life, right? But we are now also acutely aware that they pose environmental challenges, which now need sustainable solutions. And so a lot of work into understanding the environmental pollutions has been done in the field of ocean sciences, right? Because there we see there's visible evidence of plastic pollution. One of these examples is the Great Pacific Garbage Patch. If you haven't heard about it, I would suggest looking it up immediately. This Great Pacific Garbage Patch is actually due to ocean currents, right, which have essentially converged many of the runoff from rivers and waterways from the mainland into this region in the Pacific. And so you can see there's this huge masses of plastic pollution just sitting on the top of the ocean, which you can see from space. And so this is an image of this Great Pacific Garbage Patch. The ocean sciences field has done lots of work regarding this. Specifically, there's a nice review paper that looks at the different types of plastics that have ended up in this convergent space, right? Notably, there's these large megaplastics, right, which have not been broken down at all. But then it goes all the way down to microplastics that they're able to quantify. And we can see that the microplastics are on the order of several tons of pollution just sitting in the ocean right there. But what about the plastics we don't see, right? This is where aerosol science comes in. When we think about what's smaller than microplastics, there are nanoplastics. And some of these micro nanoplastics have been identified in the remote areas like Antarctica and the Arctica and the Pyrenees Mountains. That's very true. In addition to that, we see that there's also been an increase, especially since 2015, in the number of published articles that have identified microplastics in the atmosphere, right? And so it's now 2025. There's been this review by O'Brien really indicates that there's been kind of this exponential growth and an understanding that plastics are not just in the ocean, but they're also in the air as well. Another figure from that paper shows the different types of concentrations of these plastics, microplastics, that can be found in the ocean, in this left panel right here, in outdoor locations and in indoor locations across the world. Notably, you'll see that the concentration of microplastics in the ocean is under this 200 microplastics per meter cubed. But in some outdoor and indoor measurements, we see significantly more concentrations of microplastics in the air. So plastics have been identified in both indoor and outdoor air sources. In a work recently published in 2024, they also tried to understand the global transport of these microplastics in the air. That is, if we look at the different sizes, whether it's 1 micron versus 50 microns, or the total particle mass versus the total particle count, we see that microplastics are able to be transported across land and even in the remote places like Antarctica and the Arctic. So much of the study has looked at microplastics. Why? Because we know that when it comes to nano sizes pose significant analytical challenges for accurate detection. That is, conventional spectrometry, FTIR, spectroscopy, Raman spectroscopy are unable to characterize submicron particles. You essentially need a lot more mass to detect chemically some of these components. So when the particles are very small, we need a greater concentration to really identify that it is a nanoplastic. And so we know this in aerosol science, and we've known this for quite a bit. We look at number distribution versus volume/mass distribution all the time. This is a figure from Seinfeld and Pandas, Atmospheric Chemistry and Physics textbook, the 2016 version, where it shows essentially if we look at our number size distribution here as a function of diameter, we see in this image up here that the number concentration shows a lot of small particles, and we see very few large particles in this distribution. However, if we transform to a volume distribution, and mass is just volume times the density, if the density is known, we see that these particles, which were negligible in number at high diameters, actually contribute a large mass or volume. And the opposite is true. That is, the particles that we had a lot of in number that were very small actually have negligible mass that are small. And so this question of particle number versus particle mass, hopefully you've had many of these discussions if you're aerosol scientists where you are fundamental discussions in the aerosol science field. And so we pose that some of these questions are fundamental questions that need to be discussed in the nanoplastics world as well. So, indeed, aerosol techniques hold promise to understand nanoplastics, not just microplastics. And so there have been recent studies that have shown that there's consumer products that leach trillions of micro and nanoplastics. And so I wanted to highlight the work of Chris Zangmeister and Jimmy Radney from NIST. They published a paper, I want to say 2022, that looked at common, simple, single-user consumer plastic products. And so in this study, what they do is they get coffee cups and other types of cups that are actually lined with polyethylene. They pour different temperatures of hot water into these cups, and then they take the solution and they make a spray, right? Which is what we do a lot of in aerosol science. And they're able to find that there's these trillions of nanoplastics that are leached just by simply pouring water into a coffee cup. Right? And so by using aerosol techniques in this study, they're able to quantify not just the microplastics, but also the nanoplastics as well. And so there's a lot of potential for us aerosol folks to join this discussion, especially when it comes to nanoplastics. Because quite honestly, the size and the amount of nanoplastics released into the environment is still unknown. Much of the discussion is in microplastics, I should say. So if we don't know exactly how much nanoplastic is released, but we know that if they're small enough, right, small particles tend to stay in the air, it's possible that these small particles can also impact cloud formation and climate. And how is that? Well, to understand that, we need to understand droplets 101. That is, if you have any dry particle, right? Let's say in this case about 30 nanometers, and you expose it to different amounts of water vapor, the y-axis is increasing amounts of water vapor, what you find is that you get a particle that begins to swell. It reaches a value of a critical supersaturation above which the droplet continuously grows. And so what we know about this process is that the particle initial size and the particle chemistry does affect how the droplet grows. In addition to that, we know that a surface is required for droplets to form in the atmosphere and for cloud droplets to form. And so particles in the atmosphere provide that surface. In addition to that, the hygroscopicity, which is the ability to uptake water, can describe how well some of these particles uptake water. And so we know that the particle hygroscopicity, the particle size, and the chemistry are what we need to know and to understand droplet formation and cloud formation. So the question now becomes, if airborne nanoplastics exist, right, can we describe the affinity for cloud droplet formation? And so this is kind of where we started back in Actually, we started this project. It was published in 2024, but we may have started around 2021, I would say. Time escapes me. And this is the technical work that we were asked to discuss today. So the hygroscopicity of nanoplastic particles, implications for cloud formation and climate, which is published in Aerosol Science and Technology. Now, this work was done by my former PhD students, the first author being Dr. Chunning Mao, who is at NIST, Dr. Kanish Gohil at NCAR, and Dr. Devansh Rastogi, who's currently at Intel, and was supported by research funded by the National Science Foundation. So we're very grateful for that funding that allowed us to explore this fundamental science as to if nanoplastics can contribute to cloud droplet formation. So let's get into it. So for the study, we looked at 3 different types of plastics. That is low-density polyethylene, LDPE. We know it to be a lightweight, flexible, soft plastics. It's the stuff that's used in bubble wrap, right? And I've also provided its monomer unit here. We also looked at PVC, polyvinyl chloride. We know polyvinyl chloride is highly durable. If most people think of it as in the piping that's used in housing and construction, it's actually the 3rd most used plastic after polyethylene and polypropylene. So it is used globally everywhere. The 3rd one we looked at is polyethylene, terephthalate, or PET. Again, this is another highly durable plastic. It's what you use in your water bottles. It's clear, chemical resistant, and quite economical to make. It's actually the most recycled plastic that we have. All these 3 polymers are considered to be hydrophobic polymers. That is, they were engineered to repel water, and they are known to resist interaction with polar solvents, and water is a polar solvent. So how we did the study is that we took about 0.3 grams of each of these plastics, and we placed them into 200 milliliters of ultra-purified water. And so we acquired these samples commercially, right? They're typically 99+% grade versions of these plastics. And what we did is that we just placed them in solution. And so if you look carefully, you can see that the pellets, LDPE, which is lighter than water, actually float on top of the solution, whereas PET, which has a density of 1.38 greater than water, drops to the bottom. And that's also true for PVC as well. And so what we analyze is essentially the effluent, this solution right here, where you do not see any of the pellets or the particles at all in solution. And we use that as a spray to then atomize. So that's what we did. That is, we took that solution, right, without those pellets, and we essentially pass it through an atomizer. And from that atomizer, we create this spray of droplets. And then the spray of droplets is then passed through a diffusional dryer. And then as it passes through the dryer, we get these dry aerosol particles. This is a common technique that we use in the aerosol science world, especially when we're trying to generate particles in lab. From here, we can do many different things with the aerosols that are generated. For this study, we use a scanning mobility particle sizer, or SMPS. That is, we classified with its electrical mobility with the DMA, and we took the particle concentration with a condensation particle counter. I'm going to take a little sidestep during this talk. In addition to this, we actually also did TEM deposition. We wanted to visualize the types of particles that were coming from the spray, what kind of aerosol we were generating from these plastics. And so our TEM results show that LDPE, right, can create very spherical particles on the order of 50 nanometers or less. But as we increase the particle size, we get these kind of agglomerates of LDPE particles that were leached into solution. We see something similar for PVC and also for PET. That is, the really smallest particles tend to be more spherical, but we're getting some type of particles just from leached just by putting product into ultra purified water solution. Okay, was my sidestep. So back onto the particles again. In addition to doing the sizing, we typically do cloud condensation nuclei measurements with a CCN counter in parallel. And so what we get from the CCN counter when we run in parallel with the condensation particle counter is that as we increase the particle size, as we go from 20 to 40 to 60 nanometers and onward, what we do is we change the activation ratio. That is the number of CCN to CN, goes from 0 to 1, right? I love this figure from Raymond and Pandas because it clearly shows as you increase the particle diameter, there becomes a point above which all the particles activate and form droplets. And so we refer to this as a critical diameter. And this critical diameter changes for the different supersaturations. What's neat about that data is that if you have that critical diameter and if you have the supersaturation, you can plot it in log space, and you get what we know are these capicola theory descriptions of the solute hygroscopicity. So what do I mean by that? If we look at the critical supersaturation as a function of dry diameter, hygroscopicity can go from essentially 0 to very high, above 1 in some cases. And so for ammonium sulfate, which we know to be inorganic, highly soluble, it has a kappa value about 0.6, whereas something that's like SOA, secondary organic aerosol, it's somewhat hygroscopic, but it doesn't love water all that well. It's around 0.2. And for something that's wettable, but not very hygroscopic, it's close to 0. Now, the key part about this, and I'll get to this later on as well, is that capicola theory assumes that essentially the solute, the aerosol itself, contributes essentially its molar volume to the dissolution of the droplet, which actually activates more droplet growth. So I'll come back to that solution because we're talking about plastics, and that may not necessarily be the case. So for the study, we're interested in the droplet activation of these 3 plastics. In addition, we also threw in cellulose. So cellulose we thought was a nice comparison because it's mainly used to produce paper products. Furthermore, we know when we use these paper products, like when we wipe up spills in the kitchen, cellulose itself is insoluble, but it really likes water, right? That's why we're able to use paper towels and to mop up messes, but it doesn't kind of disintegrate the towel because it's insoluble. So it's a nice comparison compared to the plastics. How would it be if we compared it to essentially paper products? So let's see what we get. So in this figure, we see the supersaturation as a function of dry diameter. And I've plotted here essentially ammonium sulfate, which has a kappa 0.6, I mentioned, and something that's a really large polymer, right? It's a kappa of 0.002. How we get this large polymer is that we assume that this really huge molecular weight, because it has a huge molecular weight, it actually drives the hygroscopicity down. When we take the measurements of our LDPE, PVC, and PET with cellulose, we see it lies somewhere within this space. In fact, on average, the experimental data suggests the kappa values are about 0.5 for the nanoplastics. We then did a deeper dive into understanding how well, essentially, some of these assumptions for capicola hygroscopicity fit our experimental data. What we see is if we use traditional Colloy theory, is that sometimes it doesn't get it quite right. That is, for these nanoplastics, we see that the experimental data shows a size dependence. That is, it starts off higher, and then as it goes up in diameter size, it goes down in hygroscopicity. But capicola hygroscopicity is supposed to be constant regardless of the size. So something else is going on here that we should probably explore. When we look at cellulose, cellulose actually has a lower hygroscopicity than the hydrophobic polymers. That is, it likes water less than some of these nanoplastics that were leached into solution, which was very odd at the time. But we'll get down to some suggestions as to why that is. So again, I mentioned traditional color theory assumes that the aerosol itself dissolves and contributes to the droplet growth. But what if the aerosol is not water soluble? What do we use? Well, we actually have some models to help explain this. So to understand how the models work, we need to understand the basics of droplet growth again. That is, the supersaturation is actually a function of what we call the water activity, which describes the interactions of the solute with the water. And that is what drives its hygroscopicity. And so Peters and Kreidenweiss 2007, really, they provided this parameterization based on this kappa value and the molar volume of the solute and water as a parameterization for water activity. And so what we know through color theory is that the intrinsic color theory, which is what I plotted in the original graphs where kappa was 0.002, is really a function of its molecular weight and its density of that solute property, in addition to its Van't Hoff factor, which for most organics is 1. And so when the molecular weight is really, really huge, essentially, I think I got to flip these. And when the molecular weight is really, really huge, the kappa really should go down. And so we see this within our data sets, and we see that for inorganic, highly soluble salts, kappa really works well. But when you have solubilities that are not water solubilities that are very low or effectively water insoluble, this kappa color theory should not be applied. And there's several studies that go through this. All right, so what could be applied? Well, there's an additional theory called Frenkel-Halsey-Hill absorption theory. It's essentially a Langmuir absorption that says, instead of dissolving that core, what we're going to do is that we're going to now condense on the surface of that core. And this Langmuir isotherm can be described by two parameters, an A-B parameter, which describes essentially the interaction from the surface to that first water vapor molecule, and also that first layer to the outer layer of the droplet, which influences how much can absorb onto that surface. We know that this FHH theory really works well for things like mineral dust and black carbon. And there's several studies that have applied, especially this droplet growth, to insoluble aerosol. What we did earlier from this nanoplastic study is that we actually defined a hygroscopicity parameter based off this absorption isotherm. So let's see how it applies to our nanoplastics. When we look at the hygroscopicity as a function of diameter now applying FHH, which is the absorption theory, we see really good agreement for our nanoplastics and also for cellulose as well. So in this case, again, the absorption mechanism really implies that the size and the total surface area really play an important part in the water uptake. And it agrees well with not just the data, but the model actually agrees well with the data, I should say. So again, all particles types do not dissolve in this version. Okay, but we believe them to be polymers, right? And what we know about polymers is that polymers can swell in the presence of water. So do we have a model that describes that? And again, we do. It's called FHK, Flory-Huggins Kohler theory. So Flory-Huggins Kohler theory was first presented by Peters in 2006 and 2009. And what it does in that model is it shows that the water activity can now be described by these polymer interactions, the Flory-Huggins theory, which is where that comes from. And essentially, there's additional parameters that are related to the excess Gibbs energy for dissolution and also to the entropy contribution, which is what you get from the swelling. What's neat about this swelling ratio is that, again, it's a function of the molar volume. If we know the density, it's really a function of the molecular weights. And so one can infer molecular weights with known densities from this polymer theory. And so we have a previous paper that had done this for biodegradable hydrophilic substances like polyethylene glycol, which is used in drug delivery. We were interested in how these drug delivery polymers could swell. And so in that paper, we looked at those types of polymers. In addition, we were able to then present a hygroscopicity simplification for the FHK for those types of aerosols as well. So let me give this a quick summary. That is, we have 3 different types of models that we can apply. That is traditional Kohler theory, which assumes everything dissolves. We have total insoluble theory, which is FHH, absorption theory, which assumes that the core stays intact. And we have FHK, which is Flory-Huggins Kohler theory, which assumes that the aerosol behaves as a polymer that can swell in the presence of water. And in all these cases, as I say, we have a theoretical kappa that we can derive from the experimental data, and we also have a theoretical kappa that we can derive from first principles. And so some of these relates to all those papers where we show all 3 of these. But how does it apply to the nanoplastics? Well, when we look at FHK, and for this paper, we assumed a fixed interaction parameter, that is a chi of 0.5. It appears to agree well, this polymer theory, for LDPE and also for PVC. For the lower hygroscopicity materials, such as PET and cellulose, we get more deviation from this theoretical FHK line, right? Okay, so it's not so great. So we say in this paper that you should probably apply absorption theory, which worked well for all the products, right? But then again, how we applied absorption theory is that there were 2 parameters. There was an A and B parameter, whereas FHK only had 1 parameter because we fixed the interaction parameter. And the key to life is the more parameters that you have, the more you can make a fit. So FHK did not fit as well because we only had 1 parameter. But more importantly, what we're able to do with FHK is that we can guess molecular weight from the solute term. So Chuning did that. That is, from the data, you can do essentially a regression that estimates the molecular weight that would produce that kind of hygroscopicity. And so what we find is that for LDPE, the estimated molecular weight is about 62 grams per mole. Why is that important? Well, if you think of the monomer unit for LDPE, these 2 carbons and the 4 hydrogens, it has about a 28 gram per mole subunit molecular weight, which suggests that there are about 2 to 3 monomers in the nanoplastic that's leached from material that we generated. This suggests that LDPE and even PVC and PET, they're not polymers, but they're actually oligomers, right? So that colors the discussion in some way, right? It is not these units that have 100 or more subunits. They have 2 to 3 that are being leached from solution. In addition to that, we can look at the other properties that we obtained for these materials. We found that the kappa values of cellulose were actually lower than that of the plastics, which suggests that cellulose likes water less than some of these nanoplastics. That's one thing. Another thing is the densities of cellulose were higher than that of the plastics. And so when we think about the densities of these aerosols or solutes, the difference between the particle and the air, the density of the particle in the air, is what drives the buoyant forces, right? And so the smaller the density, the more likely you are to travel further in the fluid, and in this case, in the atmosphere. So these plastics can actually travel further than something that was cellulose-like particle, right? So again, these plastics are likely to be oligomeric, they're quite hygroscopic, and they can travel really far. So that brings us to some of the conclusions of some of this work, which is that nanoplastic aerosols are wettable and they're hygroscopic. We're able to show that in our measurements, and we're also able to show that now in our predictions. which indicates that the wet deposition is actually a plausible route for the removal of plastics in the atmosphere. Originally, when we gathered that freshly small fallen snow, we weren't quite sure how these plastics were able to get to such remote areas. But we now see that when we have tiny aerosols that are oligomeric in nature, we can actually have them uptake water and form droplets. More work needs to be done in understanding how they can potentially form ice nuclei, right? Whether it's by immersion freezing or some other process. But it is possible that these nanoplastics, like water, we assume that the bulk properties are hydrophobic. And as you saw, as the diameter increases, the hygroscopicity goes to 0. But when we are at these really small sizes, they have a higher affinity for water. And lastly, we know that less dense plastics may also be transported further, not just in the fluid that's the atmosphere, but also the fluid that's the ocean. And so understanding the density and that density difference can also help us explain the transport. So I wanted to end with highlighting some other work that's been put out there in terms of the hygroscopicity of these nanoplastics that have come out as well. Specifically, the group of Elijah Schnitzler, who showed that if you now have these nanoplastics, you can have SOA that condenses on them, and that also changes the hygroscopicity of these particles. And work by Yue Zhang that's been showed that if you photooxidize some of these particles, you can actually make them twice as hygroscopic just by aging these particles. So again, we just looked at the nanoplastics directly that were leached, but there's a whole new world of aerosol science that looks into photooxidation and aging of these particles in different ways and how they could also influence clouds and climate. Lastly, I want to show this figure from O'Brien et al., which is a review. If you have not seen it, I suggest taking a look at it. It talks about all the different ways in which microplastics can enter the atmosphere. And again, the discussion mainly focuses on microplastics because in terms of detection, we need enough mass, right? And so microplastics have been the discussion currently, right? But there are nanoplastics that do exist. Maybe they're oligomeric, not polymeric, but they are leached into aqueous processes, and they can travel through the air as well. And so there's so many opportunities, I think, for aerosol scientists to engage in this field of nanoplastics, which is only growing and growing as time moves on. So that brings me to the end of this lecture. Again, I want to highlight the work of my former students who all engaged and did so much work for this project, especially Dr. Chunning Mao, who was an architect, who was the architect of this work, Dr. Gohill, who did a lot of the modeling, and Dr. Rastogi, who did the TM analysis for this. They have moved on to greener pastures, but their work still has impact and influence that we continue to expand upon in my lab currently. So I thank them for all their work. It is truly their work that I've shown today, and I open up the floor for any questions that the audience may have.
Thank you so much for that fantastic talk. I can take any questions from the audience. You can raise your hand or post in the chat that you have a question. Okay, maybe I have one to start off while people are typing. I think this is so interesting. I'm curious about considering like uh when people think about like wildfires, for example, and like the traditional sort of like tracers for wildfires are very like cellulose combustion products, like levoglucosan, and like using that as sort of like an indicator of like how the reach of the wildfire plume gets. when you have an urban fire, for example, like in the winter fires in LA, and you have a lot of these potentially like leachates from plastics, like in insulation and industrial processes, also in the smoke plume. Um, I I guess, do you have any opinions about like a sort of deconvoluting like traditional understandings of like how um aerosol transport works versus like now this new understanding of like the fundamentally different processes and properties of like sort of oligomeric nanoplastics?
Sure, Aaron, this is such a loaded question. I think, especially nowadays, we're talking more about, the urban wildland interface, right? It's not simply just cellulosic or lignin materials that burn
Mhm.
in these wildfires, especially when they come close to homes, right? And so what are the different types of emissions that occur? That's what I'm hearing in the question. And I know there's folks who do research in this area, but we need more research in the area, right? Um, that basically stated what are the compounds, what are some of these emerging pollutants, now that we have plastics that are located in almost everything that we have, like how do they burn and how do those emissions influence not just local but regional air quality. I'm not quite sure, right, but I do know that the more information that we have, the more we can talk about things like toxicity, and the more things we can talk about the health implications of those types of particles.
Awesome. Thank you. Yeah, super interesting. I saw Steph's question in the chat first, so I'll read it out. And then I'll get to the hands in that are raised. So thank you for the fascinating and accessible presentation, science communication. We love it. My question is, did you use new plastics or aged plastics in your study?
Yeah, so I call them new plastics, right? These are those that were directly leached by placing them in water. And then we aerosolize them. We did not photooxidize them. We did not add SOA to them, right? Aging in the atmosphere can change particles in many ways. And so these were just the newly leached plastics.
Great. And then I think I saw Ruchen's hand first.
Yes. Hi. Thank you for your very interesting presentation. I'm Richard from Colorado State University. I have two questions. First one is a technical question. Just want to ask you how you prepare those microplastic. So you just brought some plastic and put in the ultrapure water. Do you ultrasonic it or just it leaching overnight and then you aerosolize, then you nebulize these solutions to get those particles?
That's the scary and beautiful part about this. We don't do
Okay.
any additional. We just put it in water, okay? And we
Okay.
get these very small distributions of nanoplastics. That's all we do.
Okay, cool. Interesting. The second question is about the Flory-Hawkins theory. I saw you try to estimate their molecular weight based on this theory, and very surprising, their molecular weight very low, just like some inorganic molecular weight around 100 is surprising. So, but I have questions about the I think chi and phi, some parameter in this theory. Uh, I tried to use Flory-Hawkins. If I know the molecular weight and I can fit my measure data and to retrieve those chi and phi, right? So I guess you assume some chi and phi value. So I wonder how you use this value and how confidence on these two values.
Yeah, we've since moved on. We've since moved on. In this paper, we assumed that the chi was equal to 0.5, and the original Flory-Huggins kappa Cola theory parameterization suggests that if you have a soluble polymer, right, this chi value is about 0.5, right? But I now know that making that assumption that it is water soluble is probably not the best. I'll say this, right? And so some
Yeah.
of the work that we hope to submit shortly does not fix chi. If you
Oh,
now have chi to be a free variable, you have another degree of freedom, right?
yeah.
Therefore, you can fit it with the data better. Now, we have
Cool.
typically 5 or 6 data points that look at critical supersaturation and dry diameter. And so because we have all those data points, we now have each data point is an additional equation, right? So we have, let's say, 6 equations, and now we have 2 variables. And so we can then iterate to find the variable
Yeah.
to use. So that's how we do that. Hopefully that answered your question.
Okay. Yeah. Looking forward to your new application. Thank you very much. Very interesting.
Awesome. And then I think Heidi's hand was next. Okay, there.
There it goes. Sorry, it froze for a second. That was an excellent talk, very interesting. I was wondering if I may have missed it, but did you measure or do you have an estimate of the concentration of nanoplastics that are left in the leachate, the supernatant?
We do. We do. Our goal was to put that in another paper, right? Because hygroscopicity tends to be intrinsic value, doesn't matter how many particles that there are. But we do see different amounts of those. Maybe I could show you a slide or two. So in this one, we know how much we get from background water. And then we also see that when we put LDPE in, we get an additional set of particles. And this actually changes with temperature and other things like that. So we do know how many particles that we do get out, and we subtract the background and other things like that. But yes, it's a lot.
That is. Thank you.
Okay. We have a question in the chat that says, wouldn't you expect these small oligomers to be volatile? In the case of PE, these would be butane derivatives.
That's a great question. The molecular weights that we have are in that 100 gram per mole range, which are condensable, right? They are condensable. They're heavy enough that they're not necessarily, I would say, gas phase size molecules, right? When we think about ammonium sulfate, it's about, I should know this stuff in my head, like 54 grams per mole. So I think the molecular weights are large enough that I do not expect them all to be volatile. It's curious that there are oligomers, not polymers, right? And so those who work with polymers say they're so large that, they're not going to like water, right? And the truth is, if it was that large, right, if it was such a large molecular weight, it would be extremely hydrophobic. But because they're these smaller units, we know that smaller molecules tend to interact with water more readily. Yes, it's not going to be a polymer, it's likely to be a oligomer. But I'm not quite sure about the volatility of that. I do think they're condensable phase.
I wonder if something about the leaching process stabilizes it in aqueous solution before it has the opportunity. I don't know. Interesting.
Yeah, I think this is where more studies need to be, right? You know, to really identify what are some of the diffusion characteristics,
Yeah.
right? Of these materials that are leaching out.
And then great answer. We have a good question. What changes in the hygroscopicity during the weathering process?
What changes in I can give more detail for that question, Satish. Weathering can mean a lot of things. I would say making it a smaller unit actually drives its hygroscopicity up. But if you can provide more context to that question, that'd be great.
Yeah, Satish, if you want to drop more context or like some other details of what you're thinking in the chat, maybe we can loop back to it, but I'll move on to the next one if that's okay for now.
Yeah.
Okay. We have incredible work. How long each of plastic sample is submerged? Oh, how long is each plastic sample submerged in water to let it leach out before taking a sample for aerosolization?
I think
Yeah.
I think it's a few hours. I think I think it was reported in the paper, but again, nowadays I sit in my office too much. But I'll have to confirm that with you later. But it's just you put the sample in for a few hours, you let it sit, and then you can aerosolize it.
And another comment there, this is from Sahir Gagran. So thank you so much to Professor Awuku for highlighting our work in the presentation. Yay. Oh, we have fun here. And then we have a hand raised from Matt Hart.
Hello. Thank you. That was a really good, timely talk too. I'm Matt Hart from NRL. We've met before. So we're currently starting some work where we're finding normally hydrophobic material in the ocean, like dust, and it's micron size stuff. When it combines with salt, it suddenly turns into a very hydrophilic particle. And it seems like another pathway for, I don't see why plastics wouldn't be any different. I mean, we're more interested in the dust from what we've seen. But it's also a pathway, I think, for larger particles maybe than nanoparticles to combine them with something that's very hydrophilic. We're talking about particles that are churned up from like the sea spray and bubbles and naturally thrown into the air combined with salt. So I was wondering if you had any ideas about that and how much easier it would be to model. And thank you.
Sure. So what we know about the soluble components is that they do a lot to drive the interactions with water. And so it's not just the bulk volume composition, but it's also the internal morphology. And so we have some work that looks at essentially particle morphology, coatings, and other things like that, or where they're partially engulfed, and how that modifies essentially its ability to form a droplet. So all of that plays a role. You're right down the street, Matt. I can always come down one of these days. When thinking about hygroscopicity, when thinking about droplet formation, yes, I tried to allude to this because this study was really just, I should say, the nascent particles that came from the plastics, right? But there's work from Sahir and others that have aged these particles. And so when you add different components, how does that modify its overall ability? I think more work needs to be done in that area as well. So we just looked at like a single composition, but the things in the atmosphere are always multiple compositions. They need to be addressed as well.
Yeah. All right. Thank you. Yeah. Just heads up, if the decision comes through that we can continue with this kind of work, we'll probably be calling you and inviting you back down again.
Please do.
Okay. Thanks.
Great. I think that got through all of the comments that we have. If you have more questions, I'm sure that Dr. Asa-Awuku is reachable somewhere. So this is a really interesting talk and inspired a lot of great discussion. I think that's sort of indicative of how relevant and pertinent the topic of micro and nanoplastics is, and considering their hygroscopicity and behavior in the atmosphere. So thank you so much for talking to about this test today.
Thank you again, Erin. It was a pleasure. AAR is my home, professional home, so I always love contributing to the science that occurs here, and it was a pleasure, and it was an honor to submit to ASNT, and I hope everybody does as well. This was a great opportunity to talk to everybody.